Dr. Bill Goodman. He's presented before about his composites. He's going to be talking about the nanocomposites and 3D printing and robotic manufacturing. This was at the request of Steve Moretto that he was to present. There's some interesting things that they're doing and hoping to accomplish with their partnership. Dr. Bill, going to turn it over to you.
Meg. Good morning and good afternoon to all the attendees. Particularly thankful for all those from the components, the war fighters, and great to be on the forum with you again, Eugene. You're doing something great for the United States of America with the forum. Meg. I'm going to do a presentation today. For those of you who don't know me, I'm the CEO and CTO for Goodman Technologies. It's an 8+ year old small business. We specialize in making nanomaterials for the most extreme environments on or off the planet Earth. Today, I'm going to focus on replacement of steel and aluminum in shipbuilding using artificial intelligence empowered additive robotic manufacturing. I'll tell you a little bit about the company, describe our manufacturing processes. Then I'm going to show you examples of composites and properties that we've made for the Department of Defense customers and NASA. I'll talk a little bit about applications for the Navy in terms of shipbuilding. Some of the applications are louvers, mission modules, bridge wings, masts, magazine armor, high temperature exhaust systems, and we're looking to scale to the size that would accommodate submarines and large ships in the future. I'll talk a little bit about considerations for the industrial base and our plan for putting part of that industrial base in Florida. This is the usual cover slide, and on this cover slide, down in the corner is our AI avatar. I usually have the avatar describe how we use artificial intelligence in the company, but doesn't really work well on Teams, so you don't get to see the talking dummy today. But what I will do is tell you a little bit about us. So going back to about 2017, we've had 25 SBIR, STTR awards. Out of the 25 of those, there have been 9 that are Phase II projects. In addition to those, we've also had 2 Phase III transitions, one for AFRL and the Space Force, and one with GE Aerospace. Additionally, we've had 4 grants with 2 national laboratories, so 2 each with Sandia and 2 each with Los Alamos. We have put together an enviable intellectual property portfolio. There are multiple patents that have been issued, and there are multiple patents on the come, and then there's a variety that we've licensed from our university partner that allows us to have any use case anywhere in the world. We have a number of strategic partners. A couple of those, the top 3 are AI-related companies. So there's AI Strategies, their 9High platform. There's Vantic, who does business with the government on both sides of the Atlantic. And then Johnny Walker is the CEO of Hollow Technologies, who will be following me today. In the area of large-scale gigawatt type energy applications, we have Ghost as a partner. For composites, we have Parejo. For large silicon carbide space systems. We have ECM for CubeSats. We have Grand Systems in Taiwan, and we have a number of universities that we partner with. The company has been very successful in terms of winning technology awards in the state of New Mexico. That's where we were headquartered up until the beginning of 2023. The company's been a UCLA Alumni Bruin 100 business in 2024. And we've participated in a number of the accelerators and incubators, including the SBA's Emerging Leaders Program, H4X Labs for the Navy. They have a platform called Launch, which addresses commercialization of technologies developed for the Navy. We were in the first cohort of National Security Innovation Network. We participated in the Navy STP this past year at Sea, Air, and Space in the DC area. And that's where I met Mr. Moretto. We were also in the first cohort for New Space Nexus Igniter. That's an accelerator incubator for space companies. And we were a participant this summer in an experiment with the 4th Fleet off Key West as part of the Navy's SEC program. This is just a pictorial. In the bottom right corner is basically all the government components, agencies that we work with: Missile Defense Agency, Office of Naval Research, Naval Air Warfare Center, the Air Force Nuke Weapons Center, Space Force, even DARPA. Universities across the top: Wichita State, University of Hawaii, New Mexico Tech, University of New Mexico, Anderson School of Management, and New Space Nexus is considered a research institute. We've had several of the prime contractors as subcontractors to us, so we can either prime or sub for various things. The vision for the company: we use AI across the boards. We use several different types of AI. So not only do we use the machine learning things that you might be familiar with, ChatGPT is the one that everybody knows about, but we also use generative AI, and that's provided by Vantic. And then I'm not going to steal Mr. Walker's thunder, but holosales is another one of our disruptive capabilities. But we have in these hexagons, we have both commercial and government products. And our partnership with Ghost allows us to be a green company where all our electricity is going to be produced by wind and solar and stored in storage systems. And all of these systems will use Goodman Technologies GTNANO ruggedized materials. And that's how we scale and become a green and empowered company. In terms of the AI process, the starting point for us is with AI Strategies and their 9-High platform. It provides a guidance system that sits above the artificial intelligence and machine language and actually collaborates with me, the human subject matter expert. And the objective of 9-High is to burn down the risk in the supply chain, as well as accelerating technology development. So typically on an engineering project, you have a principal investigator, you have a program manager, task managers. The AI agents that are in the 9-High platform are designed to fill in those the roles and complement the human subject matter experts that are in those roles. And the reason it's called 9-High is there are 3 areas: product technology, team and stakeholders, and market applications. And if you divide those up, there's 9 categories: appeal, value, reliability, personnel, planning and process, finance, size and scope, demand, access and delivery. Those are the areas where 5 GPT-powered design guidance agents bring guidance to the program. So in terms of Goodman Technologies, we like to focus on the most critical problems for extreme environments. It's typically weight, cost, and survivability. For electronic systems, we make shielding for space, air, land, and sea. We've done ground testing of our lighter than aluminum shielding against weapons effect, and that will be flying care of the Air Force Research Laboratory at the International Space Station in February. In the area of hypersonics, as you know, we're third in a three-horse race against the Chinese and Russian with deployed systems. Our NASA Orion capsule failed upon reentry, and of course, we do have a mission to perform global strike. I'm going to show you some of the things we did for NASA to make hypersonic structures. And then the last area we're dealing with is energy efficiency. And typically we're reducing weight and improving the resiliency of the materials that go into systems. So these have applications in energy, in ships, and drones, and many other things. So here's a look at what we've done. We've actually added our material systems to robotic systems at Wichita State University. What you're seeing in these pictures is our manufacturing of a 20-inch prototype reentry system for NASA. So that would be the underside of a space capsule. We use fiber patch placement. And I was informed that we were the first on the planet to make a fabric ceramic matrix composite prepreg and implement that. And that was actually by the manufacturer of the robotic end effector that was used to apply our prepreg to this part. And on the far right, you see our printer circled in green. We can extrude any kind of nano paste, no matter how thick it is. We get 500 PSI pushed out the end of that printer nozzle, and it's rugged and robust. It had to be because we're pushing silicon carbide, the third hardest material on the planet. Normally with additive, you get XYZ axis or maybe XR, and theta. But when you add the printer onto the end of a robot, you get all the degrees of freedom with the robot. And so on this particular part, we had to print vertical sidewalls, and I'll show you that in a minute, as well as going around a radius edge and then the top. But let me show you how fast this stuff works. This is real-time fiber patch placement. Picks one up, slaps it down, picks one up, slaps it down, picks one up, slaps it down. It's that fast. And then over here is the printer in action. And we've done the vertical sidewall, and we went up around the radius, and now we're getting to the central part of the hemisphere. That's also a reasonably fast process. And nice thing about robots is they work 365, 24/7. They require a little bit of maintenance, but they're great. One of the technologies I developed is
Hey, Bill.
Yes.
So I wanted to stop you. If you could stop every so often, make sure to see if anybody has any questions, because we don't want to get past a point if somebody has a question. We want the interaction to be live and pertinent to what you're discussing. And with that,
Right.
JD has raised his hand. Go ahead, JD.
Thank you. I was just curious. I saw that you have an entry there for the F-35 as one of your initiatives, talking about engines and fuselage. What all? Can you dive into that a little bit more, please?
Yes, so on Phase I and Phase II SBIR for the Office of Naval Research, we competed against 5 companies, 2 or 3 of which were publicly traded. And after Phase I, we were selected as the only one that met naval requirements. So we made 3 different composite systems, and we added our nanoforest, which I was just about to describe, to it. And what the nanoforest does is this. We call it ANT, Aligned Nanoforest Technologies. And what it is it's carbon nanotubes, but they're aligned. And what I usually describe a composite system as is an Oreo cookie. So the strong part of the Oreo is the cookie shell, the weak part's the cream filling, and it's easy to rip apart at the cream filling. You just twist it, it comes apart. Kind of the same in laminate composites. So in the middle here, there's a circle. That circle is a single carbon fiber in a composite. In this case, it's about 7 microns. They're typically 7 to 10 microns in diameter. And next to it, you see almost what looks like a star field. Those are individual carbon nanotubes that are occupying that cream filling or matrix-rich zone between the layers of composite where there's no fibers. And by doing that, we get composites that are lighter, tougher, have better tolerances, and that reduces the amount of scrap. Because carbon nanotubes are electrically conductive, this can be made into shielding against EMP, EMI, X-rays. It can also be used to make low observable composites like on the F-35 and the F-22. So for the Navy, we made 3 composite systems. We made a carbon epoxy that was reinforced with the nanoforest, with the ANT technology, and we made that a hell of a lot better. We also then took bismuth imide, which is the skin of the aircraft, and we improved upon the material properties of that composite system. And finally, on the inside of the engines, you have stator blades, which are made of metal, and some high temperature polyimides, and we made those a lot better. Well, how much better can you get with GTNANO and ANT technology? Here's an example of a silicon carbide and epoxy, a pristine composite, which has no nano in it, and then enhanced with GTNANO. And you can see that for various key properties that you can get from single digit to triple digit improvements in performance. This is a much better alternative to making knitted fabrics, because when you bind layers of fabric together with knitting, you're going to run a needle through there and you're going to break fibers. And it's also a better alternative to braiding, because when you braid things like in a rope or a piece of yarn, you're stretching things in one part of the fiber and compressing in the other. So you're actually introducing a complex stress state. So there are 3 composite systems that we have addressed for the F-35. Here's another type of fabric that is not knit and is not braided, but it is actually fabricated much like one would fabricate a tablecloth. And in this case, the 3D fabric, it doesn't use 6,000 or 12,000 or 24,000 needles to make the fabric. It uses 5, one for X, Y, Z directions, and one for plus or minus theta. And this new technology can be made to make 3-dimensional parts like you see here. It's been done in pan, it's been done in pitch. It's been done in alumina, ceramic, and it's been done in nickel-on, silicon carbide fabric. The other nice thing that can be done with this technology is once you impregnate to make a dense composite, you can then go back and machine it into shape. And if I were to show you this turbine blade as an example here up in the right corner, you would see that there are no overlapping fibers. They all have their individual space, so it avoids the damage to the fibers. For NASA, this is the fabric ceramic matrix composite prepreg. This is a 6-SiC composite. We arc jet tested at Ames Research Center. We tested this part more than once. We demonstrated that it didn't lose any weight, it didn't erode, and that it was therefore reusable. The Phase II contract, I showed you, that was the scale up, and that was the robotic manufacturing part of the system. The same technology is relevant to global strike. For the Air Force and the Nuke Weapons Center, we made some shielding out of the composite. And this composite is lower mass than aluminum, and it would make a great structure to replace aluminum or titanium in CubeSats, because now everything inside that box is going to be shielded against radiation effects. And we have also used printing to make mirrors and structures to build a telescope. And so we're actually doing a prototype demonstration for the Space Force right now. So this 3D rendering, that telescope structure exists right now. The 3D printed primary mirror exists right now. And the shielding, as I mentioned, it's gone through X-ray, gamma ray, proton testing, thermal vacuum testing. I can't show you a lot of that data because that would be CUI and export control. But what I will show you is we did put this in a vacuum chamber. It worked quite well. This was a low Earth orbit that we went through.
Bill, Jeremy's got a question.
Yes, I'm not able to see it. I'm on a single screen.
Yeah.
So yeah, just type in. Yep.
So the quick question on the mirror, was that the surface of that mirror your material as well, or were you scaffolding for a mirror surface?
Oh no, this is 100% silicon carbide. I guess the thing that I should point out is, compared to any 3D printed mirrors that you've seen by other players, they're all reaction bonded silicon carbide, which means that they printed a porous silicon carbide body, and then they melt infiltrated with silicon, and then they had to go back and polish it. With our process, we have 100% silicon carbide. Everything is made dense from the get-go. We're able to substantially replicate a polished surface to get something that has a specular finish on it. And then we are able to do some touch polishing to get the shiny mirror surface that you see here. And we've done that up to 31 centimeters in diameter with an off-axis parabola. And that was on a whole separate NASA Phase II effort. Did that answer your question, Jeremy?
Yes, it did. That's really neat. Can you dope the material so it's spectrally selective in what it reflects and what it absorbs?
So you do that with the optical coating that you put on the surface of the mirror. But what we have done with the mirror substrates, we've added graphene, we've added carbon nanotubes to change the resistivity of the material. And when we do that, we can control the CTE to reduce it. Silicon carbide's pretty good material, but it's not a zero CTE material like ultra low expansion glass or zero Dura. But I did tailor some material that would operate at the L2 orbits in space. So the James Webb Space Telescope sits at the second Lagrangian point between the Earth and the Sun. And basically it's a stationary orbit. And because it looks out into deep space, the operational temperature that it sees is about 25 Kelvin. So there are some games with nano we can do to change the properties of materials, as you suggest.
Thank you.
Well, this chart normally has a plot on it that shows data, but since we're in a non-CUI environment, you're not going to see that. But what I can tell you is that we tested the space shielding at the University of New Mexico against a gamma source that went from about 122 kVs up to 1.4 MeVs. And again, our material is lighter than aluminum, but it's far more effective at stopping X-rays and gamma rays than aluminum is. Likewise, we took the material out to Cal Davis to the Crocker Nuclear Facility. We hit it with high energy protons that one would see in a low Earth orbit environment. And the table indicates that the dose that we saw with our shielding was better than what aluminum would allow you. This is the telescope model that I showed you in that CubeSat. So it was additively manufactured. So these were the individual pieces. And then here's how the telescope came together to become a monolith. And in this case, this is a CSIC material. That's carbon fiber reinforced silicon carbide. It is a siliconized material. So here's the telescope structure after being siliconized. And so this is the design that can scale to larger sizes or smaller sizes. And we made this design, the idea is, think of what Henry Ford did for manufacturing the automobile. He had a assembly line that brought the automobile to the workers rather than the workers going to the automobile. So at the end of our assembly line comes off telescopes. And then what one can do is we've made the design telescope such that with a zoom system, we can see things that are in proximity, not far away, or things that are infinitely far. And our design allows the use of different cameras on the back side of the telescope. And so that could be monochrome, that could be color, that could be hyperspectral. You build the same part over and over again, it brings down the cost. Now you can customize it, and with the shielding that we have on the outside of it, it allows off-the-shelf cameras that do not have radiation-hardened electronics.
You can't make this shit up. So you don't have limos bringing industry.
Somebody's off mute.
But I love the comment, you can't make this shit up. It's true, because I did it. So, but getting back to the Navy and what we done, this was kind of the introductory slide, and this is the one I'm allowed to show public release data for. We have pristine composites with none of our nanoforest technology in it, and then we have some that do. And we looked at two high temperature composite systems. These are polyimides. They can handle about 700 degrees Fahrenheit, which is hotter than the broiler in your kitchen oven. And what we show is that that we made the composites tougher than they were without our materials. We looked at a number of other material properties. You see some of those down in that table below in the right corner. And again, you see double digit improvements, in some cases triple digit improvements to the fracture toughness when you add our technology. This was the skin of the airplane. And again, we showed that that we made the skins substantially tougher. And that's good if there's foreign object debris on the flight deck, carrier anyway, bounces up in your aircraft. You don't want to take it out of service. If you want to make them tougher, if you want to reduce the scrap so that they're bring down the life cycle cost of the system. These are very desirable properties. These are just some of the some of the accomplishments. So I can't give you all of the accomplishments here, but anyhow, we did see another important improvement is in dampening. So when something gets struck by a load, whether it's acoustic or impact, they ring. We reduce ring down with our material. Now, there's a lot of uses for the Navy. Places where composite has been looked at are the Zumwalt composite deckhouse, the fan shrouds for the LCACs, which are an amphibious vehicle, and then the composite mass. I mentioned earlier that we did an experiment this summer. It was the day before Helene entered the Gulf and devastated Florida. We were out on the USNS Burlington, and we flew this drone. It's called an Aviator. It's an amphibious drone. It can fly in the air, it can fly underwater. And we hung a variety of our composites set up as radar reflectors off the bottom of it and tracked the system with the air search radar. So that was done in conjunction with the Fourth Fleet. We looked at some fireproof composites because obviously if things are going to catch on fire during wartime or even during peacetime, there are some considerations for composites, and one of them is smoke and toxicity. And so we partnered with Hexcel to take their material, which is lighter than steel and lighter than aluminum, and has very comparable or even superior properties to those metals. And we've looked at improving with our material. And one of the first things we looked at was louvers on the ship. This would be basically a crawl, walk, run approach to reducing weight on ships. And so we took a look at this for PO USC at the request of NAVC and Mr. Moretto, and how this might be used in littoral combat ships. And so, compared to steel, a composite would give you a 41% weight saving, and compared to aluminum, you can get an 80% weight saving while not sacrificing other key properties. And this is just a repeat to just show you these systems. Again, another place where composites can save some weight on ships is for transport modules. These are the transport modules that are used on the LCACs. And this is a fine example. A prototype was made in 2015 by a small business. They did a first production article in 2017. When they started, they were a 6-person company in 2016. And within 5 years, they had over 600 million in book contracts. And these were just for ordinary fiberglass coated balsa wood composites. These weren't even nanocomposites. So it shows that there's a viable pathway for success for our company and what we're doing. One of the other areas that we're looking at after louvers would be for containers. And containers, when they have things in them, like this one here, are called mission modules. But basically, containers in the past are essentially modified ISO containers. Again, we can make something that's much, much lighter and can stand up to the requirements of these kinds of containers. So this was just a little bit more detail on a program to first make the walls of the container. That's the crawl part. And then the walk part is actually making the container system itself. And so, steel's pretty low cost, but again, we're fighting against weight. And so we have a way to make things lots lighter. And our hope is that will be lower cost than aluminum. And aluminum is a lot more expensive than the steel. One of the things we looked at for the Navy was, what the U.S. supply chain looks like, because, speaking to the choir here, we're trying to improve our industrial base, defense industrial base here in the United States. And if you look at where all the composites are made, the U.S. itself only accounts for about 20% of the market share. So you could add in market share from Japan, Belgium, Korea. We need to do a lot better than what we've done to date. We really sold ourselves short with some of our policies and things we've done. The next thing we did was you have to convince people that small businesses can do things, and that was the purpose of me showing you that what one small company did with phenolics and balsa wood. Here's a look right out of our business plan for a nanoforest pilot plant and how we scale it up over time. And so again, this is a pilot plant, and by adding reactors in, basically bootstrapping, we can get to 4.6 million square feet a year for this material. By having multiple plants, you just multiply the number of plants times this number. And by adding money, you accelerate this output. So we can greatly accelerate this with Defense Production Act Title III. And we have submitted a proposal, a very large proposal, with a lot of the team members that you saw earlier on, to get some matching funds to do a public-private infrastructure play. And this private-public infrastructure play, it's described here. It is a factory of the future just because of all the security that it does and all the different materials that it can make to provide for the defense industrial base. And I'm happy to show it here because honestly, nobody can compete with this. We have a great team of people in the company. Mathis Shinnick, our CFO, is a serial entrepreneur. He's wore every hat in the C-suite. He worked for all the major investment banks on Wall Street before going to Europe and doing European desks, and then before going to Hong Kong and working the Hong Kong desk. John Vo was the director of global manufacturing for Tesla. He set up the first gigafactory. He also set up the first car factories, the C, the S, and the X-class factories. Mike Whitmer is our chief visioneering officer. He's a Mensa. He's an expert in AR, VR, XR, and MR, AI, ML, and deep learning, NFTs, DAOs, RFIDs, big data, Web3, digital assets. Ron Unruh is our COO. Ron was the first duly warranted contracts and acquisition officer for the entire Department of Defense. He's done 16 joint ventures, the companies he worked for before us. And then finally, I'll just tell you that when you need nanocomposite materials for extreme environments, you better call Goodman. And I thank you, and I'll take any questions now.
All right, thank you, Bill. Okay, so Mr. Weaver, go ahead, please.
Yeah, hey, thanks for that presentation. Just out of curiosity, because I'm a wireless guy, knowing that some of those materials you described are conductive, have you done any work in like conformal antennas or extruding custom-made antennas or integrated antennas into these fabrics?
So what we did was we made for the Air Force Nuclear Weapons Center a complementary split ring resonator that would allow for a very specific frequency to transmit the shielding to allow for command and control capability of an aeroshell.
So essentially shielding it from everything except for that particular frequency. Cool.
Yep. Yeah. So to make composite antennas that have better skin depth than aluminum is entirely possible. Yes, and it'll be lighter than aluminum. So the other nice thing is with the composites, you can actually replicate surfaces for those types of RF antennas that I pretty much see in your mind right now. Yeah.
Thanks. Very cool.
All right. Anyone else? Steve, did you want to add anything?
Yeah, that antenna question is pretty good because he's looking at masts. I'm wondering, could the masts could be integrated into the antenna? And what would you need to scale up to it, like a Navy size mast?
So in terms of the composite, the large robotic systems that I showed you are deployed in lots of different companies across the globe. The best set of stuff that I've seen was at Wichita State University, which is one of our university partners, and they have the ability to make things composites up to 70 feet in length. Think wind turbine blades. So it really comes down to, your curing process. So there are, some require autoclaves, but there are a lot of out of autoclave composites that are available these days as well. And those are used by a lot of the system primes. So I don't think scale is the big challenge so much as it is getting a repeatable and high quality material that that meets the drawing and then can survive the environments they're going to be exposed to.
So it sounds like you got
Go ahead, Steve.
a material that's 40% lighter than aluminum, stronger than steel, can
And 40% lighter than steel and 80% better than aluminum.
Okay, I thought it was stronger than steel, lighter than aluminum.
It's
And it can absorb radar. It's heat resistant. It's been tested with the NASA standards for outgassing. So it could be on submarines potentially with some validation.
EMP as well.
Is radar absorbent. So it sort of sounds like you could, it does everything better than the existing materials. So if you built a ship out of this, it would be sort of like giant going from wood to steel in terms of the amount of capability it could add to the Navy ships and submarines.
I would like to think that.
Might have to have larger ballast tanks though, right? If it's so light.
So what would be the timeline? What would need to be done to get to the point where we could build a ship out of this material?
Money and people. So I think we're in a what's the new words for it? The great power competition. If this is like if we were back in World War II, and you look at all the industrialists that stepped forward to convert their commercial factories into wartime manufacturing facilities, I think we're kind of about in the same place in history. You know, we're rhyming in time, and so I think that's you know, if I'm the industrialist, that's I need the resources to put this all into place.
So, Bill, what about ITAR? I mean, the community does have European, you know, like the UK Defense Ministry, Israeli Defense Ministry, other people from Greek. Would is this transferable with our partners?
So I've actually had the opportunity to brief NATO. I've had the opportunity to brief the Joint Staff J8 Directorate. I thought I saw Howard Meyer come in. He was one of the persons I briefed. We recently submitted a white paper to a call from the DoD to support Ukraine. And we do have a number of international partners already. So yeah, there are the means and mechanisms to cooperate with our allies. And I am an expert on export control and commodity jurisdictions, and so yeah, there is yeah, that's all there's ways to do all that.
Okay, so are you talking to Carter Rock at all? Because when I was at Carter Rock, I was part of the topside signatures, did a lot of work on the Zoom Vault for, you know, testing and adapting and retesting.
So I'll tell you, a lot has happened within the last 2 months. I know we've talked with Crane. I just can't remember if I did an individual brief with Carterack or not.
Okay. I can put you in touch with the CTO there. You remind me, and because you may not want to talk to Carterack, you may want to talk to, it's like PMW 693 or something like that. I can't remember exactly. It's been a couple years that they support. So that's going to be out of NAVC headquarters. So let me reach out. Actually, I'll reach out to the CTO at NAVC headquarters and see what she can help with, and probably just introduce you to her.
Appreciate that.
All right, Dave Maraska, you had your hand up.
Yes, sir. Thank you. Dr. Bill, great presentation as always. Question, you had proposed into OSD previously, right? And you had a proposal that was basketed. So essentially it's gotten through competition, correct?
So we submitted it was it's not the so we submitted to the Cornerstone OTA. That's in review right now. We also submitted the 15-page white paper to the Defense Industrial Base Consortium OTA.
Right, that's what it was. Yeah, okay.
Yep, and we were selected for that, and they had some higher priority things that they wanted to do, but yeah, we're basically sitting on the sidelines waiting for that one to be funded.
But I believe you were basketed, so you've satisfied competition, and if you had folks with funding available, they wouldn't have to go through any further competition, correct? With that,
Well,
but I guess what my question is that specific proposal that was accepted and basketed, would that cover what Mr. Moretto brought up earlier as far as producing, say, a ship of a certain size? Would that funding align to that, or would that not cover what you would need for a ship? Over.
So the nice thing is that proposal is for the same scale up of capabilities. So the answer is yes, we could use that equipment, those processes to build ship components.
Okay, thank you.
It's a good question.
All right. Any other questions?
Just a comment on that OTA submission that was sounds like it was basketed. I can confirm because I run an OTA myself that yeah, if that is the case, then anybody in the DoD that has money could just go pick that up and execute it fairly quickly without having to go through the whole solicitation and recompete process. So start hitting up your friends at the end of the fiscal year when they've got money burning a hole in their pocket.
You hear that, Joe? Joe Gamez? You hear? Can you? If you know anybody,
I'm
Joe,
sorry, can you repeat that?
go ahead. Tell.
I was just confirming, you know, if the OTA that they submitted to and had the proposal basketed, if it's anything like all the other OTAs that I'm aware of, anybody at the DoD that has funding can go and pick that up, and it's pre-solicited and pre-competed, and they can just move forward with it as is. And then I made the comment that that's particularly enticing to program managers at the end of a fiscal year.
Yep. Yes, thank you. I got you.
All right, Felicity, you had a question for Josh, actually.
Oh yeah, he just mentioned that he ran an OCA. I was curious if
yeah, so I'm the AOR for the Spectrum Forward OTA with the National Spectrum Consortium.
Oh, cool. Okay, thanks.
Yep.
All right. Anyone else?
I have a question.
Go ahead, Brian.
Dr. Goodman, if you had a couple wishes, dream projects, what would you like to start out with? And then my second question is, if you could apply your products to some scale models for testing, whether that be antennas or ships, how soon could you do that?
The dream projects, my big thing, going back 2 decades, is weapons effect shielding. Back in 2010, there was a DoD 5051 that addresses CBNE, and it said that every system that the United States makes has to survive a nuclear event. And the big problem that scares the hell out of me is that we're in a world where everything is going electric. Okay, and when I give a quick pitch, one of the things I always say is, you know, that every aspect of our lives depends upon a space electronic system. There isn't a single thing we can do down here on the planet Earth without our space electronic systems. And that includes Uber Eats. You can't do GPS, you can't do radio, you can't do TV, you can't do international banking. So our satellites are the most vulnerable thing that we have, but yet it's the thing that where we still have a little bit of superiority over the, I hate calling them peers, but it is what it is. Not my words, but you know, that's my big thing. I want to be able to shield us so that we can survive. So that's my big wish. as far as other things, there is a fiber system that I would like to do some things with. It's called basalt. It's made from a volcanic rock. It's a non-conductor. It's very tough. It's very lightweight, and I also 3D print armor shielding. Hot strike plates. So there are some interesting ceramic matrix composites. There's some interesting things I'd like to look at for hypersonics and high temperatures using basalt. So that's on my list of things I'd like to explore. Does that answer your question?
Yeah, and then I was curious if someone wanted to test your samples instead of building a large, say, boat, maybe it's a lot easier to build a very small prototype and then compare it to other boats in a wave pool. How easy is that?
Oh, that's so we've made a couple little white paper class things that are of interest to the Navy to do, and yeah, that's a perfectly feasible way to go about doing things.
All right. Well, thank you, Bill. Appreciate it. And a lot of good contacts here. I want to catch up with you because there's a couple of people I want to introduce you to as well. And in addition to who I've introduced you to in the past. One question I had for you, Dr. Bill. So there's a company that has been in touch with me about, or I'm working with actually, that is doing a UV cured, they have a UV curing process. I can't get into any more than that. What is it, the epoxy or whatever, is that what makes, what changes it from being UV curable, or having a 3-day cure? And
there's different ways to cure materials. So Hughes Research Laboratory in Malibu, California is one of the places that's done 3D curing with materials like silicon oxycarbide as an example. The problem with that is how do you build your part? So if you're going to add things into the epoxy, you're essentially going to attenuate the UV radiation, and so it limits the manufacturing.
Okay.
So one of the innovations that I've done with composites is to get out of vacuum chambers, thermal vacuum furnaces, right?
Right.
And I use microwave curing as an example. And we're able to reduce the time to make parts from months and years down to hours to days or so, using the microwave to do the curing. So
yeah, that's what their application does, is it reduces it from days to hours.
It's another form of high energy radiation that makes things react and combine. So the one thing that one usually sees with UV curing, in the case of silicon carbide, is dramatic shrinkage. The parts that Hughes Research Laboratory was making shrank 30%.
Wow.
So you have to actually design that into your manufacturing process. The good news was it shrank isotropically. So not anisotropically. But the stuff that we make is we actually have a less than 0.1% shrinkage in our material and get 100% silicon carbide.
Okay. All right. Thank you for that.
Roger.
All right.
Thanks, Eugene.
So yeah, not a problem. Appreciate you being here.